Hi, good evening. So let's start the class. I will start sharing my screen. All right, so I hope you can see my screen now. Yeah. Um, cool. So welcome to the 11th session of the NPTEL course Essentials of Data Science with R Software. And um, so so we've done 10 sessions, and after today's, there's just one more remaining. So before we start the session, do you have any questions, anything you want to ask, tell, suggest? No. No? Okay, all right. Fine. So I will start with discussing what was taught this week. Please feel free to ask any questions, or if something's not clear, just tell me to repeat that. Or all right. So um, you can unmute yourself, or you can put it in the chat box. And once we're done with the discussion, we'll then go and solve some questions. That would be really helpful for this week's assignment. Okay. All right. Um, so last week we had discussed a few parameters about how to test if the estimator for a parameter is good. So this week we are talking about two more, that is consistency and sufficiency. So we've been talking about the difference between a population and a sample, right? So again, the idea is that we want to estimate a population parameter. Think of it as mu or lambda, or oftentimes it's also denoted as theta, as you would see, as you've seen in the last week and in this week. Um, so, but something that we have already established in the previous weeks is that the more the sample is, the better should be that estimation. So consistency of estimators is completely hinging on this aspect. So it's saying that as the sample size increases, and we denote sample size by n. So as n is increasing, as n is tending to infinity, the value of that estimator should become more and more close to the parameter that is being estimated. Okay, so if you denote, so for example, here, so whatever it is that we are estimating, whether it's one thing or whether it's multiple things, right? So whatever is that estimate, that minus what the actual ideal thing is, which we don't know, but the difference between the two of them. So this notation basically means that that difference, if you're taking an absolute, because let's say the actual value is 10. So whether you estimate it as 9.9 or you estimate it as 10.1, that difference is what we are more interested in, which is that 0.1 difference. So that difference, so the absolute value, if it's greater than a certain number, so epsilon is typically a small positive number. So that difference, the probability of that difference being a large number is almost zero, as n is tending to infinity. Likewise, that difference, there's a very high chance of that difference being smaller than a number. So that probability is really high as n is tending to infinity. So this notation, whether you write theta, whether you write x, it doesn't matter. It's the concept that we are more interested in. So long story short, as you increase n, the value of that estimator should become more and more close to what is being estimated. Therefore, and we know that this theta hat, that estimator is itself a random variable, right? So how would we know that an estimator is close to its original value? We can demarcate this by taking the variance of it, right? So what we are doing is we're taking a variance of that estimate, and that variance should tend to zero as n is tending to infinity. And we've seen previously that MSE is a combination of variance and biasness, right? So either of these terms. So we, for simplicity's sake, we are only interested in the variance of the estimator. All right. So if the variance goes to zero, then as n tends to infinity, then we are sure that we are talking about a consistent estimator. Okay. So for example, if the random variable is, let's say if it's a normally distributed random variable, we know if you define a new random variable, which is the average, then the mean, that would be mu, and the new variance. So let's say this is going to be like, 1 second. So this should be square here. So the new variance is going to be the old variance divided by n. And now you can see that as n increases, the value of this variance is going to go to 0, right? Because it's in the denominator. So that's very simple, back of the hand rule, that if n is in the denominator, then as n increases, that value is going to decrease. So you can simply say that the estimator that we're looking at is consistent. And we'll see a few examples, but it's going to be as simple as this. All right. So that's the first thing, consistency. Then we come to the second thing, which is the sufficiency. So, so basically, sufficiency means that, so we've been talking about, let's say, so a sample has, so there are multiple samples that you take often, right? So for example, you can have, in this example, there are two random variables, and there could be a certain combination of the random variable that you're looking at to estimate a parameter. I'll show you another example in the next slide. So, so what we want to do is that we want to use up all the random variables in a certain way. Okay. So it's sufficiently using the information that is known. It's not leaving out on information. That is what sufficiency is talking about here. So the way we do it is, there is a theorem which is called the Neyman-Fisher factorization theorem. So we'll break it down. It's again a very simple concept. It looks complicated here, but don't worry. So what we are doing is, the first thing is we are factorizing. Okay. So factorizing means splitting something into, so you remember it's the concept of HCF, right? Highest common factor. So what you're doing is, or basically making factors. So let's say if you're looking at the number 6, its factors are going to be 2 and 3. If you exclude 1 and that number itself, the other factors are 2 and 3. So the product of 2 and 3 gives you that number back. So that's what we are doing here. Factorization means splitting the value into a product of 2 or more components. So what we are going to do here is, so let's say this is your sample. And this was the PDF of any distribution. It be normal, binomial, Bernoulli, whatever it be. So what you can do is, so what you're doing is, you're taking the product of all probabilities, which is this thing right here, and you are splitting it into two functions. So these two functions are basically denoted as G and H. So now H here is going to be a function solely of x's. T is also a function of x's. And so first of all, there are going to be two functions, one containing the original random variables and the other one with the random variable and the parameter. Okay, please let me know in case you're not following. So this one also is based on x. This one also has x in it. And this is the one that has the parameter. So the first requirement is that there has to be one function which is independent of the parameter, which is independent of theta. That's one function. The other function should have both x and theta, right? So one of those contains the parameter and the random variable. And this t here, this thing which is in the form of x, this form directly is what is going to estimate the theta. Okay. So the first step is, so let's walk through it once more. So we have a random variable with some PDF. Let's start with the example of a normal random variable, normally distributed random variable. And for simplicity's sake, here we are going to say that mu is mu and sigma square is actually 1. Okay, you remember the formula of the normal distribution. Now what we are doing, instead of sigma and sigma square, we are substituting 1. So we get a certain form of the normal distribution, right? So let me just write it down so that it's clear. Okay, this one, and yeah, this should be okay. So the form is 1/2 root by exponential minus half xi minus mu whole square. Okay, so this is the form, right? This thing. Now what we are going to do is we are going to, so here we had xi, so we are going to multiply, so this is one probability, right? This is one probability density function. We are going to multiply all the probability density functions. So x1, x2, xn, right? And when you multiply all of those, so you're taking a product. So this is what you get, right? 1 upon 2 root pi, this becomes this form, right? This is being multiplied n times. So this is the nth power. And exponential anything, you add up the powers, they get added up, right? So here you're adding up the powers, minus 1 by 2 comes out. And then this entire thing, you can so this entire thing, you can do a summation of it. Now you can just rearrange the whole thing. So here you get a term which is x square. Here you get a term which is only x, and you get some constant terms also. So now compare it to this form. So there is one term that in the product, there is one term which does not have the parameter. So this is that h. Now the rest of the term which has both the parameter and the x, there the term of x, whatever the term of x looks like, that directly is going to estimate your parameter. Did this make sense? Would you like me to explain it again, or is this making sense?
Okay, I understand.
Okay, perfect, great. So this is how we are doing the factorization. And we will see some examples later on. Okay, fine. So this ends one aspect of estimation of parameters. But now there are two more ways in which the parameters can be estimated. Okay, so we will take a look at the method of moments and the maximum likelihood estimation. So this is known as estimating the central tendencies. Again, it's again the same thing, something like the mean or the expectation, right? It's all revolving around the same concept. So just to revise, this one and the next slide are, I've just taken slides from, I think, week 4 or week 5, right? So this is what expectation is, right? So this one's for continuous random variable, this one's for the discrete one. And again, expectation can, it can again be done not just for the original random variable, but for any function of that random variable also. And more importantly, the thing that we are going to use that we have seen in this week is about raw moments. So rth moment of x about 0. So anything about 0 would be called the raw moment. And if it's about a certain other number, then that's called the central moment. But we are more interested in raw moments right now, right? So it is of this form. And so if you try and solve this, so we'd mostly be interested in the first and the second raw moment in the upcoming slides. So that's what we are going to do. So mu prime 1 and mu prime 2 is what we are looking at. So the way we are denoting it is this, right? So anything with prime is going to be the raw moment, and anything without the prime is like the central moment. And so mu, just like we have mu and x bar to denote population and sample means, here we are going to use mu for the population, and m we are going to use for the sample moments. Okay, so we are again doing the same thing. We want to estimate the population moment via the sample moment. So you can see here the way it's being denoted is exactly the same as we saw a couple of slides back, right? So the difference, the probability that the difference is greater than a certain number is 0 as more and more sample is taken. And the probability that those two numbers are converging, they're almost the same, is the very high as the numbers are increasing. So same thing. So at methods of moments, what we want to do So the method of moments allows you to estimate all parameters, right? So there can be any number of parameters that a distribution has, right? So for example, uniform distribution can have two parameters. All mostly uniform distribution has two parameters, right? The lower limit and the upper limit. But for simplicity's sake, in this example, we have taken lower limit to be 0 and upper limit is any value, right? So typically you say it A and B, but here we are calling it 0 and theta. So 0 is known. So we are just left with one unknown. That's this one. In case of Bernoulli trial, there is just one unknown, right? Which is the probability of success. So that's P. In exponential, there's again one parameter, which is lambda. In normal, there are two parameters, right? Which is mu and sigma square. Okay. So the way we are going to do it is, it's a simple concept of algebra that if you want to solve, if you have n random variables, you need n equations, right? If you remember in school, there were topics such as linear equation in one variable, system of linear equations. So you'll have two variables or three variables. So you need to have as many equations as the number of variables. So like this. So in case of uniform distribution, since there was only one parameter we want to estimate, we'll just take the first raw moment. And we know the first raw moment from this slide, we know it is equal to mu. It is equal to the expectation value, right? So for a uniform distribution, this is the value of expectation. This is, until here is what you know. So this needs to be equated, right? So this is the sample mean that you can calculate. And theta by 2 is going to be the population expectation or population mean. So we will just want to equate sample mean and population mean. And we want to estimate theta. So we just rearrange. So theta by 2 is equal to x bar. Therefore, theta is equal to 2x bar. Right? Okay. Same thing for Bernoulli. The expectation value is P. That's how P is defined. So P is equal to x bar. That's it. Simple. For exponential, we know the expectation is 1 by lambda. So we are equating 1 by lambda to x bar. So lambda is equal to 1 by x bar. In case of normal distribution, we would need two equations. We'll take the first and the second raw moments. The first raw moment, that is equal to mu. You equate it to x bar. The second raw moment, that is mu square plus sigma square. And that you equate to the second, this one, right? This is the, instead of x bar, you will have the summation of xi squares, the average of xi squares, basically. Right? Is this making sense? We'll see some examples, so it should become even more clear, but let me know in case you have some confusion here. All good?
Yes.
Okay, cool. If this is done, then we come on to the second way to estimate the central tendency. So here what we want to do is, so we want to choose a certain, so basically what we want to do is we want to have a particular value of theta of that parameter such that given these values, so given these values, the probability of occurrence of those values is the largest. So what we are basically going to do is something similar to what we did in the Fisher factorization theorem. So what we are going to do here is we are going to take a product of the probabilities, right? So this symbol indicates product, right? This capital pi. So when we take the product, you can just rearrange it. So binomial, so the Bernoulli trial, it takes the form of the binomial principle, something on those lines. That term that you get, that term which has all the xi's, that term is what we define as the likelihood function. And this likelihood function, this is some combination of probabilities. So we want the probabilities to be the largest. So we want this term to be the largest as well. So maxima. And if you remember, the way to find out maxima is to differentiate it. So the reason is, so let's say whenever we so whenever we have a plot, okay, whatever the plot is, at maximas, this value, okay, the slope at any maxima or minima also, the slope is 0, right? And the slope is given by the differentiation. So if you differentiate this term once, that should be equal to 0. Now we don't know whether if it's 0, if that 0 indicates whether it's maxima or minima. So you double differentiate it. And then the sign is going to tell you whether it's maxima or minima. So just for simplicity sake again, you can either differentiate this term directly or you can differentiate its log. Either way, it's going to give you the same result. Because log is just, sometimes it simplifies the form that we are looking at. Okay. So for case of Bernoulli, this is what the form is going to look like. That must be differentiated. And I don't have it explicitly in these slides, but the calculation was shown to some extent in the lecture videos. Okay. Likewise, for a uniform distribution, if again we're taking the same type of uniform distribution between 0 and theta, so the probability is of the form 1 by theta. And if you take a product of all the things, so it's going to be 1 by theta into 1 by theta into 1 by theta n times. This is what this is. Again, this needs to be maximized. So you differentiate it or you differentiate the log of this. Okay. So that's the concept of maximum likelihood estimation. That was the second part, right? So first part was consistency and sufficiency. Second part was method of moments and maximum likelihood estimation. And the third part that was discussed this week was the confidence intervals. Okay. So until now, we have been looking at point estimates. We have been looking at point estimates of mu. We have been looking at point estimates of sigma square also, or lambda or theta, right? Sometimes we may want to look at intervals. That is, what is the probability, or not probability, but we would like to estimate that there is at least some probability, let's say 95% probability or 0.95 probability, that a value is going to lie within a certain range. Okay. So the smaller the interval, so let's say, so again, something like the examples that were also given in the class is that, how much time is it going to take a person to go from here to there? So let's say if we're not talking about, if the timing of, let's say if the type of traffic does not change too much on those roads that you're taking, every time that you go, you would probably take around 10 minutes, around 12 minutes. So 10 to 12 minutes. So I'm saying 10 to 12. So that range that I'm quoting is just 2. But let's say sometimes the roads are absolutely empty and sometimes there's going to be so much traffic on it. So it might take you 10 minutes, but it might also take you 25 minutes. Okay, let's say something like that. So the range is indicating it's like a 15-minute range. So that length of that interval is reflecting the uncertainty, right? So that range is sort of telling you both the mean and the variance. Okay. And the way we define this range, we say that the parameter theta that we are looking at, that is covered by this CI. CI is short for confidence interval. So the parameter is covered by CI, by confidence intervals, around the lower and the upper limits with a probability of 1 by alpha. That means it's and not that the probability of the interval containing the parameter is that. So it's a slightly different way. So it's not the, so basically the two sentences are the same thing, but we are not saying that what are the chances that my interval contains the parameter. Rather, we want to estimate what is the confidence interval around the parameter itself. Okay, so the parameter is the main focus, not the interval here. Okay, so the way you find out the confidence interval is by calculating something called the pivotal quantity. The quantity itself depends on the sample, so that is x and y's and the parameter, but its probability distribution does not depend. So it is not a very complicated concept, but what I thought for the purpose of the live session at least, and it's also going to help you solve the assignment questions, I just have something like a cheat sheet here. So I'll just walk you through the whole thing. So in the classes, there were 3 examples taken. The first one was that we want to estimate the confidence interval for mu, and sigma square is known, right? So it's just, we want to estimate mu here. So since we want to estimate mu, and we're talking about normal distribution in this case. So, right. So all these examples were for normal distribution, by the way. So there were a few calculations done. You can go back to the calculations. They were explained quite a lot in detail in the class. But what happens is we finally want a confidence interval, right? We want a lower limit and an upper limit. And you know that a normal distribution is a symmetric distribution, right? So about the mean, about x bar, you can add a certain value and you subtract a certain value. So this value is the same. So when you add and subtract certain values, you get a smaller number and a larger number. Those numbers are going to tell you that 90, whatever percentage of confidence you have, that the value, that estimate of mu is going to lie there. Okay. Again, we will take some examples to see what it's doing, but let me just tell you what these numbers are. So here we said that sigma is known, right? Sigma square or sigma is known. So that's what we are denoting as sigma naught in this case. Root n is just whatever n is, you take a root n. And z alpha by 2 is the important term here. So we are looking at a certain confidence interval, right? So let's say this is what the normal distribution is. And we want that 95% should be the confidence. So this is the interval we are looking at, right? This region is 95%. Okay. So now you are left with one region here and you're left with one region here. So let's say this is area A. This is also area A. So twice of area A is equal to, that means 5%. So each A here is just 2.5%, right? So the way it says is, so if alpha is equal to 0.05, 1 minus alpha is equal to 0.95, right? So if you remember, this is how they had been denoting it, right? With the confidence interval. And since we're looking at two sides, we're looking at both sides. So the Z value here or here, we are taking it as alpha by 2. So alpha by 2 is equal to 0.025. Right? Now, so we want to find out the value of the normal distribution. Okay, I think okay, all the, whatever I had written, whatever I was noting down, it got removed, but that's okay. I'll rewrite it before uploading it. Okay, anyway, so what we were doing here is alpha by 2 is 0.025, but what is Z? We want to find the value of Z at alpha 0.025. So if you remember this thing, right? So this is the normal distribution. I can I'll just put the links to these again. So this is a normal distribution, and we are looking at a normal distribution that is a standard normal. Okay. So we want to find out the value of Z here or here. Okay. So what we can do is, so 0.025 is the probability, right? So 0.025, if I do that, I'll get the value of X as this thing. So 1.96, right? 0.025 is what I estimated, right? Since alpha was 0.05, we are looking at two sides. So this value right here is going to be 0.025, that probability. This is at the value 1.96, right? So this value of Z alpha by 2 is going to be 0.96. And you can also find it like this. In our studio, if you do a Q norm 0.975, that will also give you 1.96. It's the same thing. Because what Q norm is doing, it's actually doing the up to this point, right? So same thing, CDF, right? Okay. All right. Associated with that, there is this error term. Okay, so basically this is how we denote the error, right? The value plus minus something else. So this is exactly that error term here. You can rearrange it to get a value of n. So what we want to do is we want n to be large so that the error is really small. Okay, so what certain value of n would you want so that error is the least? So all of those can be calculated. All right. Okay. The second example, so this was the first case, right? Now we take a look at the second case here. So here also we want to estimate mu, the confidence level for mu, but now sigma square is also unknown here. So again, the derivation of this was given in the in the lecture videos. So the only difference in this case now is that we would be using the sample the sample standard variance, sorry, the sample standard deviation, which is denoted by S. And instead of a normal distribution, here we are going to look at the T distribution or the student T distribution. And again, we are going to look at alpha by 2 values here. And if you remember, the T distribution also has an additional component, which is the degrees of freedom. So the degrees of freedom is going to be 1 less than the N there. Okay, the rest of this looks very much the same. Okay, it's just that instead of normal distribution, we are now looking at the form here is going to be in the form of the T distribution. Okay, so that's the second part. The third case is now we want to estimate sigma square, but mu is known. Okay, so this time it's going to be slightly different. It's going to look different. This time we are estimating sigma square, and this is going to be of the form of chi-square distribution. And now chi-square distribution, the numerator. So again, this is the numerator is the same. So here, if you remember, if you can see here, it's symmetric. It's symmetric. This one, chi-square distribution, is not symmetric, right? So the two terms that we are looking at here, first of all, they're not like x bar plus minus because we are estimating sigma square here. So it's not plus minus anything, but these are two different terms that we are looking at altogether. Okay, so again, we'll come to the questions in a while and we'll see how to solve these. Okay, all right. There was one last topic which was introduced this week, which was how to calculate the confidence interval using R. Now, the topic of next week, that is more related to confidence intervals and hypothesis testing. And since there are no questions from the confidence interval this week in this assignment, so it's just going to be a little more complicated to discuss that this week. So if it's okay with you, we'll discuss this next week. It's just going to complete the story well. All right. If that's okay, then we can go on to the practice questions. All right. Yep. Okay. All right. Cool. So if you can have a pen and paper ready with you, we can just solve some questions. So let this go somewhere. Okay, fine. So let x1, x2 until xn be a random sample from a population with which has a normal distribution, and it has population mean mu and variance as sigma square. So now we are assuming sigma square to be known, and we are saying that the sample mean is defined like this. So there are three estimators of mu. So mu1 hat, mu2 hat, and mu3 hat. So what can you say about the consistency of these estimators? So do you remember how we are going to proceed for consistency? The hint is that it has something to do with the sample size, something to do with n. Wanna give it a try?
Yes.
Yep.
Okay.
Say that again.
We need to see like the expected value of the sample values will be equal to the parameter, and the variance of the sample observations
Yes,
tends to
correct,
zero,
correct.
and
Perfect, perfect, perfect. Right? Okay. So we want to see if the variance of these estimators, if that is tending to zero or not. Right? So what is the variance of the first term? So the variance, when you take an average, so basically what you can do is you can think about it. Okay. So variance, let's say I'm just telling you. So the variance is going to be the original variance divided by n. Okay. And the concept that I'm using here is that variance of a plus b, that's going to be equal to variance of a plus variance of b, right? And variance of NA is equal to n square variance of A. So these are the two sort of concepts that you can do in case you forget what the variance of an average is. So what we are doing when we take an average, we are adding up all the random variables and we are dividing it by n, right? So when we add up the random variables, so that's going to be n sigma square, and we're dividing it by n, we'll take n square. This n and this n cancels, so you're left with sigma square by n. This is how the variance of average comes up to be this value, right? Okay. Now that you have this value, now we are dividing it by root n. Okay. So when we're dividing this by root n, so basically you're multiplying it by 1 by root n. The variance is going to be multiplied by the square of this number. So that's going to be sigma square by n square. Right? Root n into root n is n, and this was already there. Let me know in case this is not clear, because this is a small thing, but it's just algebra, some multiplications and all. Okay. Likewise, for this case, it's going to be sigma square. That was the original n. And here we have n square in the denominator. So we'll also have the square of this again. So that's going to be 1 by n to the power 4. That's going to be sigma square by n to the power 5. Okay. So now we have these three terms, and in all the terms, you have n or some power of n in the denominator. So as n goes to infinity, that is what we are looking at. Variance of all the three terms, of all three estimators, this tends to 0, right? So all are consistent estimators. All right. Good. Okay. If this is clear, then we'll go to the next question. So here we have a random sample from a uniform distribution. So it's a normally, like it's the way you typically write a uniform distribution with like A and B, or theta 1 and theta 2. So which of the following statements is true about the sufficient estimators? Okay, so remember, so sufficient estimators is that you need to use all the terms. Okay, all the information that you can have about x1, x2, x3, xn, all of that should be used. So out of these options, so theta 1 is the minimum value, theta 2 is the largest value. So can you tell me which of these is correct? So
D.
correct, that's right. So because minimum only is not enough, maximum only is not enough, the term C here is actually reversing the two things, right? So minimum is valid for theta 1 and maximum is valid for theta 2, right? So together, these two things are important. So it's not just that both of them have to be there. I mean, both of them have to be there and they have to be there together, because estimating just one of them does not make sense. Okay, so correct, this is the right answer. Okay, now these are 4 questions actually. Okay, question 1, 2, 3, and 4. So what we are doing in each of the questions is that you have a different distribution. You have Bernoulli, you have exponential, you have normal, and you have Poisson. And we want to estimate something. So in case of Bernoulli, we want to estimate theta. For exponential, we want to estimate. So basically, this was analogous to P as you've been writing it earlier. For exponential, this theta is analogous to lambda. In case of normal distribution, here we are saying that the mean is 0 or the variance is sigma square. So we want to estimate sigma square. And for Poisson distribution, we also write that as lambda. So that's going to be, so that's theta here. Okay. So now what we want to do is we want to find out the sufficient estimator in each of these cases. So what I will do, sorry. Okay, just a second. Yeah. Okay. So so what I'll do here is I do have the answers, I think, here, but let's not look at the answers just yet. Do I have an empty slide somewhere? Okay, this one is empty. So what I'll put this one here. Okay, and let's try and solve this one by one. Okay, so okay. So we'll start off with the normal distribution. Okay, so normal distribution here, it was given of the form 0, sigma square, right? This is what the question gave you, and we wanted to estimate sigma square. So for sufficiency, we had that factorization theorem. Okay, so normal distribution is of this form, 2 by root pi, or it's root 2 by pi. Anyway, whatever that term is, exponential minus 1 by 2. This is going to be x minus 0 whole square by sigma square, right? This is the form. Okay. Now, what I want to do is I want to multiply all the xi's here. I want to multiply the PDF for all x's. So what I'll do it, I'll have this 1 by sigma square root 2 pi. I'll multiply this n times. So this gives me the power n. With an exponent, so I've e to the power something multiplied by e to the power something multiplied e to the power something. So those powers get added up. Okay. So this is going to be exponent 1 by half. The sigma square is also going to come here. And this is actually going to be xi square. Okay. So now if you remember from the factorization theorem, there's this term here which has your parameter, right? It has this parameter here and it has some form of x also, right? So whatever that form of x is, that is going to be the estimate of your parameter. That's going to be the sufficient estimator of your parameter. Okay, so you can see here. Okay, so this is the answer, right? This one. Did this make sense?
Yes.
Okay, cool. So now we'll quickly solve the other three also so that you have it for your record. Okay. So the next one, let's go and solve which one? Let's solve this, the one for Bernoulli here. Okay. Let's put it here. So we have for Bernoulli, it's of the form theta x 1 minus theta to the power 1 minus x. Right? Now we want to multiply all of those. So the first one is going to be theta. Now here the power is going to get added up. And then here what we are going to have is we'll have 1 minus theta. And here also it's going to be, we'll have 1 minus x1 plus 1 minus x2 and so on, right? So whichever term you see, in both of them, they're going to be of this form, right? Here also it's going to be of the same form. So it's going to be n minus sigma I, and here is also sigma xi, right? So therefore again, sigma xi is what we are looking at for Bernoulli. Okay, this one. So that's the sufficient estimate. Now you see, we know from our previous case that for mean 0, so sigma square, so you remember, right? Sigma square is this x minus xi minus x whole square and all divided by n, all of those, right? So it is of that form. So you can do like a sanity check to understand that, okay, what you're finding it if it's of the similar form that you are familiar with. Okay. So next one, let's do for the exponential distribution. So this is going to be of the form theta x to the power theta minus 1, right? So here also we are going to, so when you are multiplying all the probabilities, this is going to be theta to the power n. And this is going to be, so here is going to be x1 to the power theta minus 1. Then we'll have x2 to the power theta minus 1. So on and so forth until xn to the power theta minus 1. So you can write, it's going to be the product of xi's to the power theta minus 1, right? Just like you denote summation by this symbol, you denote product by this capital pi symbol, right? So again, this is the term that you're looking at. So this is the term that we get here. Okay. And the last one that we'll look at here, that's the Poisson distribution. So for Poisson distribution, let's call this in terms of lambda. So this is going to be lambda to the power x e to the power minus lambda upon x factorial. Okay. So now again, when you are going to do a product of the whole thing, so it's going to be lambda to the power summation of xi's, right? Lambda to the power x1, lambda to the power x2. And then this term right here is going to be, it's this one's a constant here. And then the denominator is going to be a product of factorials. Okay. So again, yeah. So this again is going to be the other term. So this is what we are looking at, right? So this one term here, summation. All right. So here we have estimated the sufficient parameters for the 4 distributions. Any questions for this one? All clear?
Yes.
Okay, perfect. Great. Fine. So now we want to estimate the parameter for, again, we're talking about the same distributions now, right? So again, this is your exponential distribution, right? So this is exponential, here this is binomial, this is Poisson, but now we want to use the method of moments in this case. So again, the method of moments case is as many equations as the number of parameters that have to be estimated. So in all the 3 cases, we would be taking the first raw moment, right? So we will be using mu1 prime and we'll estimate like m1 prime, so as to say. So if you remember here, so this was actually already done, right? I think, yeah, this method of moments, Bernoulli uniform exponential. Poisson, again, I think you should be able to do it, right? For Poisson, it's x is equal to lambda, right? So x bar and lambda, you can equate that. So it's going to be pretty straightforward. Okay. I just have the questions here because they're similar to the ones you have in your assignment, but they're going to be straightforward. Okay. So let me skip this for now. Okay. So now we have some questions. Okay. So this one's there are 3 or 4 questions here that are now from the topic of confidence intervals. Okay. So the first question here is that the teacher is using a random sample of 150 students from a college with a large number of students, and they're using the mean of observation to estimate the average quantitative aptitude. And assume from the past practice that sigma has this value, what can be said with probability 0.99 about the maximum error of estimate. Okay, so now the formula that we are going to use. Okay, so yeah, all right. So the formula of error, if you can check from a few slides back, that we're going to use here is Z alpha by 2 sigma by root. Okay, this is the formula of error. So first of all, we need to start looking at what all is known. So n is equal to 150 here, right? Sigma is equal to 6.2 here. And we are looking at, so here they are saying something like this probability, okay? So 1 minus alpha is equal to 0.99, okay? This is what 0.99 means. So therefore, alpha is equal to 1 minus 0.99, that is equal to 0.01. So now we want to find out, so that means alpha by 2 is equal to 0.005. So what is Z alpha by 2? All right. So to know that, we are going to go to the alpha calculator, right? The normal calculator. We'll put in 0.005 there. So let's say we'll just solve 0.005, right? So this value here, that's equal to 2.57 or 2.58, right? So when we calculate this is a 2.58. That's it. You just need to plug in these values here. So 2.58 into 6.2 divided by root of 150. Okay. This should come to something around 1.3 as far as I remember. But we can just solve this. So root of 150 is, so this is 12.25 and 2.58 into 6.2 is, this is almost 16. So right. So 16 divided by 12.25. Yeah, so that's equal to 1.3. All right. Cool. This one's, it's just you need to remember the formula and you need to find the corresponding value of Z and then just put those in, and it's straightforward. Okay. And now we would have 3 questions, one from each of the 3 cases of confidence intervals. So they're all using the same data. Something is known for something else needs to be estimated. So you either use normal distribution, t-distribution, chi-square distribution. Okay, so now the question is about a signal being transmitted and a signal being received. And there's a given mean and variance. You have been given some values. You've been given so yeah. So you want to basically find the estimate for either mu or sigma square, respectively, in each of the questions. So for the first question here, so here we want to find out the confidence interval for mu, and here it says, sorry, not this one, this one. So this is mu and the variance is 36. So this forms the case 1 type of a thing, where mu, the confidence interval for mu needs to be estimated, and sigma is 6, or you say sigma square is equal to 36, anything. And we also need n. So here it says it was sent 9 times, and these are the 5 values. Also, we need this term, right? We need a sample mean. So sample mean is going to come from here. So you need to find out the sample mean manually. So 5 plus 8.5 plus 12 plus 15 plus 7 plus 9 plus 7.5 plus 6.5 plus 10.5, that divided by 9. So you take the average, so that comes out to be 9. Okay. And again, we want to find out the two-sided 95% interval. So we go back to that cheat sheet. Okay. So it's going to be of this form. All right. Z alpha by 2 sigma by root n plus, so the confidence interval is going to be x bar plus minus Z alpha by 2 sigma by root n. Okay, so that's going to be 9 plus minus. Now, again, Z alpha by 2. So alpha is going to be 0.05. Alpha by 2 is going to be 0.025. And this one you calculate, but you can already see that this is going to be 1.96. We just saw this value. So this one value you can remember also. It's going to be 1.96. Now sigma here is 9. Root n, so n is 9, so root n is 3. So that's going to be 9 plus minus, this is 2, so this is 3.92. So the confidence interval here you get is, I already have it solved, so I'm just writing that down. So that's going to be 12.9. So this is going to be your CI. Okay.
Okay.
All right. Fine. Then we come to the next type. So again, same things. But now if you see here, the mean is also unknown and the population variance is also unknown. Okay. So now this would be, so here you want to estimate again with a confidence interval from you. So now it's going to be that second case that we saw. Okay. So again, going back. So this is the second case. Now here it's going to be it looks very similar, but now instead of normal distribution, we are going to use a t distribution. So what we'll do here, again, so what we have n. We do have this value with us, right? This is the same, but this we don't need. No, we need it. Sorry. Yeah. We need this. Okay. And we need this S value right here. Okay. So S or S square. Again, we'll calculate it from here. We want to find out the variance of this term. So you can find out the variance manually also. Okay. So S square, if you calculate, I did it using R Studio actually. So just using the function var bracket within in C as a vector, I'll give these values. So it gives me this value. So which would mean that S or standard deviation is going to be 3.08. Okay. I hope I've solved this correctly. 0.08. Yeah, this is okay. All right. So we know this. And now again, it's the same thing. So alpha is equal to 0.05. So alpha by 2 is equal to 0.025. Now what we want to calculate is T alpha by 2. And this is n minus 1. So n is 9. So this needs to be 8. So what is this value? Right? So what we'll do is, we will go to student T distribution. Yeah. So again, it's a similar looking page, right? This is degrees of freedom. We want 8 degrees of freedom. So this is what the term looks like. And now here we want it as 0.025, this value, right? The area has to be 0.025. So this one is at 2.3. Okay. So, so this is going to be, so 2.3, right? So now again, it's going to look like X bar plus minus T alpha by 2, n minus 1, S upon root n. Plug in the values. So X bar we know is 9, plus minus, this thing we calculated as 2.3. This S was calculated as 3.08, and root n is going to be 3. So 9 plus minus, now this we calculate 2.3 into 3.08 divided by 3. So that's going to be 2.36. Okay. So if you calculate this, it's going to be something like 6.63 and 11.4, something around this range. Okay. Cool.
Okay.
Okay. All right. And now I think we'll just have the last case. So this was a slightly different form. So now what we have is we have a sample of 20 bottles. So N is 20. The sample variance, so S square here, 0.0153. Now the variance of the fill volume is too large and unacceptable proportion of the volumes will be under or overfilled. We'll assume the fill volume is approximately normally distributed. And we want to find out the upper confidence interval for the variance, sigma square, right? So that becomes the last case 3 type of a thing. So mu is unknown. We don't know mu. And we want to estimate sigma square, right? So it's going to be this form, 1 minus n, n minus 1 sample, sample variance divided by the chi-square. Now here you see, so here what we have seen, this is Z alpha by 2, Z alpha by 2, T alpha by 2. So the term that is being added or subtracted is always alpha by 2, right? But here it's not so. It's alpha by 2 here, but it's 1 minus alpha by 2 at the other case. Okay. So, so what we are going to do here. Also, there is one more difference that you need to be sure. So here you see another term that we looked at, we did not focus too much on, was two-sided. Here also we saw two-sided, right? So which is why we were dividing alpha by 2. Now here it says upper confidence interval, right? So let's say if this is your chi-square distribution. So we just want this term. Yeah, right? Okay. So what we'll do here, 95% upper confidence bound. Yeah. So it's going to be like, it has to be less than a certain number. Okay. So what we'll do is we want n minus 1 s square divided by chi square 1 minus alpha. So here it's not going to be alpha by 2 or anything. It's just 1 minus alpha n minus 1. Okay. So now again, alpha here is going to be 0.05. So what we want to do here is, okay. Okay, so I think upper bound, I'm not sure, but upper bound has to indicate, I think like the minimum value or something. Lower, let me double check, but I think, so we want it to be something like, yeah, the sigma square has to be minimum this much. I'll double check and let you know. But so what we want to do is, so again, we had 20 terms here. So n minus 1 is 19. And we want it to be, so this one has to be 0.05, right? So it has to be something like this thing here. Yeah, I think I've gotten confused, but it has to be of this form. Okay. So okay, take it as at face value for now. I will confirm and let you know. So the value here of the value that x at which the interval is 0.05 is actually 10.12. Let's say 10.12. So maybe it's not this thing, but rather it has to be this thing here. Right? So here we're going to solve this as it's going to be 19 into 0.0153. And this value we just solved, that is 10.12. Okay. So again, so just solve this. 19 into 0.0153 divided by 10.12. That's equal to 0.0287. Okay. So I think this means upper confidence bound. Just give me a second. I'm just stopping this. I'm just stopping the sharing for just a minute. Okay. Anyway, so this was the last question that was there. Give me 1 minute to confirm this thing. But other than that, do we have any questions?
Well, in the third case that we were doing, like we have in both the cases alpha by 2 in the subscript of z alpha by 2, t
Yes,
alpha
yes,
by 2.
yes, yes, yes.
Yeah. Why was it 1 minus alpha here? Why
Okay, all right. Okay, so now so I'll just explain this here. So the key term here is whether we are doing a two-sided estimation or whether it is one-sided. You will see term two-sided or two-tailed or two-way estimations. Okay. So here the key term is upper or lower, right? And here in the previous cases, we saw two-sided. So it's not only valid for the third case. So the thing is, so let me draw it here. So if your confidence interval is like this, so we have a lower limit and we have an upper limit. But if instead your confidence interval is like this, so you just have a lower limit and the upper limit is infinity. So here you had this term and this term, and here you just have this term. Now, same thing. Here we are talking about, so here 2a is equal to 5%, and here it's just b is equal to 5%. Right? So if alpha is equal to 0.05, then each of these is going to be alpha by 2 and alpha by 2. But here if alpha is equal to 0.05, then this directly is 0.05. So we are talking about, so we are always saying a 95% interval. Somehow it has over the years, over calculations, 95% has become acceptable. So now this 95, is it, so the remaining bit, which is 5%, is 5% split into two areas, or is 5% just one area? If 5% is just one area, then that's it. This is the area. So which is why here we just took alpha directly. Okay. But if it is split into two areas, we'll use alpha by 2, alpha by 2.
Okay.
Okay. All right. So I will still have to confirm this upper bound thing. Maybe I've missed it somewhere, but this is how the questions are being solved. I will definitely check it and let you know. Okay. All right. So with that, we come to an end to this class. So anyway, this is all being recorded and I'll upload the PPT also to the Google Drive. And the assignment deadline is next Wednesday. And we will have the last session for this course for week 12. That's going to be on 12th of April, next Friday. Okay. So, all right. Thank you all for joining in. And good luck with the assignment, and I'll see you all next week. So, bye-bye. Good night.
Thank you, ma'am. Thank you.
All right.
Thank you.
All right. Bye-bye.